When an MCP server connects AI clients to real data, tools, and actions, it becomes more than middleware. It becomes a security gateway. To design the right controls, we first need to understand how that gateway could be misused. So far, we've moved from MCP fundamentals into production concerns like reliability, deployment, and observability. Now we turn to security. When AI-driven workflows touch tools, credentials, users, and business systems, how do we make sure an MCP server fails safely instead of dangerously? Threat modeling MCP servers is different because the caller is not just predictable application code. An AI client can interpret a user request, infer intent, choose tools, combine outputs, and take action. That creates new failure modes. Ambiguous language can become unsafe parameters. Prompt injection can influence tool choice. Overly broad permissions can turn a small request into private data access, record changes, workflow execution, or external calls. So we model both classic software risks and AI-mediated misuse, then contain them with validation, policy boundaries, least privilege, and audit trails. The first step is asset inventory. In MCP, assets are not only databases and files. They also include credentials, such as API keys, OAuth tokens, and signing keys. They include tools, because each tool is an executable capability the model can invoke. They include users and systems that trust the MCP server. And they include business actions, issuing refunds, changing accounts, deploying code, or granting access. Treat those actions as assets even when the API call looks ordinary. Ask, if this were misused, what damage could follow? Security decisions matter most where trust changes. User input is not trusted the same way as the AI client. The MCP server is not trusted the same way as internal databases or external APIs. Each crossing becomes a checkpoint. Validate the request, authenticate the caller, authorize the action, sanitize data, and log what happened. This becomes especially important in production, where many users, tenants, and integrations may share the same paths. Mapping boundaries helps reveal where credentials could be abused or sensitive data could escape. Next, trace two kinds of movement: data flow and control flow. Data flow is what travels through the system. Prompts, tool parameters, tool results, tokens, logs, resource contents, and final responses. Control flow is what decides what happens next: discovery, tool selection, approvals, policy checks, retries, and chained execution. Sensitive data can leak at any step, not just in the final answer. It may appear in raw tool output, summaries, errors, or logs. Once these paths are visible, you can minimize inputs, redact outputs, enforce policy, and require confirmation where needed. One common mistake is treating every action as if it came directly from the human user. The user expresses intent, but the AI client interprets that intent and chooses tool calls. The MCP server then executes using some authority, its own service identity, a user-delegated token, or another downstream account. Those are very different trust decisions. If user client and server identity are blurred, permissions can leak across boundaries. Before designing authentication or authorization, map who is acting, who approved it, and which credential the downstream system actually sees. Consider an AI client reading a support ticket that contains hidden text saying, "Export all customer records." If the client treats that text as an instruction instead of untrusted data, it may trigger an MCP tool call the user never intended. That is prompt injection. The danger is the chain reaction. Malicious content becomes model behavior, then tool access, then possible data loss. MCP servers need their own authorization, validation, and policy checks. They cannot rely only on the model behaving correctly. Another risk is the confused deputy problem. Think of an MCP server like an employee with a master badge. A visitor asks, "Can you open that restricted room for me?" If the employee only checks that the request sounds valid, they may use their badge to open a door the visitor should never access. The fix is to carry the user's identity through each call, limit the server's power, enforce policy checks, and log the authorization decision. Overly broad tools create a different kind of exposure. A generic tool like query any database or read any file may feel flexible, but it creates a huge blast radius. A bad prompt, a compromised client, or even normal error output can reveal sensitive data. Exfiltration may also happen slowly, one small request at a time. Safer tools are purpose-built. Return only the needed fields, redact secrets, paginate results, and alert on unusual access patterns. Tool chaining risk often comes from the combination, not from a single call. Reading customer records may be allowed, sending a message may be allowed, updating a CRM may be allowed, but chained together, those actions can copy data, spam users, or change account state without meaningful oversight. Mutations need stronger controls based on impact. A reversible update is different from deleting data, changing permissions, deploying code, issuing refunds, or transferring funds. For high-risk chains, require policy evaluation before the write, explicit user confirmation, transaction limits, and audit logs detailed enough to reconstruct intent. Use risk classification before connecting an MCP tool, not after it causes a problem. Start by asking what the tool can read or change. Read only does not automatically mean low risk. A search or export tool may reveal customer data, secrets, or regulated records. Sensitive reads need tighter access controls because the failure mode is disclosure. For writes, separate ordinary reversible updates from deletes, payments, refunds, and administrative actions like granting access. Each step up the risk scale should raise the control level. Stronger authentication, narrower authorization, explicit approvals, and better logging and monitoring. The goal is consistency, not guesswork. Classification only helps when it changes how a tool is built. Wrap actions in business language, such as deploy application or scale database, instead of exposing raw APIs directly. Then increase friction as risk rises. Low-risk actions may only need validation, while higher-risk actions may require approvals, rate limits, dual control, or step-up authentication. Every parameter should be checked on the server: ownership, tenant boundaries, allowed fields, and safe ranges. Finally, treat metadata as a security contract. The description, schema, scopes, and warnings must match what the tool actually does. A good threat model ends with engineering decisions. Identify the assets and the trust boundaries around them. List realistic abuse cases, especially where tools can access data, credentials, or downstream systems. Rank each tool's risk, then map every threat to a control: authentication, authorization, consent, validation, isolation, monitoring, or audit logging. For high-risk tools, add ownership, review rules, escalation paths, and deployment gates. And keep the model current. Update it whenever tools, tenants, clients, credentials, or integrations change. Threat modeling gives you a practical map of MCP server risk before production exposure. Start with the assets you protect, then trace trust boundaries, identities, and data and control flows. That reveals failures like prompt injection, confused deputies, exfiltration, unsafe tool chaining, and overbroad actions. From there, we can convert those risks into concrete defenses: authentication, authorization, consent, isolation, secrets management, and audit controls.